Hello everyone. I'm Fei Long. Yes. Hello everyone. Jeez. Hello. Uh, what's the problem? Okay, thank you. Okay, hello everyone. I'm Fei Long, a PhD student from Tsinghua University. Today, I will present our work on OptiFlow towards LLM-driven optimization of collective communication algorithms. This is a collaborative effort with Microsoft Research Asia and Zhongguancun Laboratory. Okay, let me start with the motivation. Collective communication is crucial in LLM training. As shown in this timeline, communication operators are interleaved with compute to exchange parameters, gradients, and activations across GPUs. Communication often takes 30% to 50% of iteration time. Thus, collective algorithm design directly dictates end-to-end performance. So this optimization is increasingly difficult. Messages sizes ranges from kilobytes to gigabytes. Cluster scales from a single node to thousands of GPUs. Long-running jobs also change model stages, GPU assignments, and parameter and parallel strategies. The best algorithm is configuration specific, so collective optimization has become a repeated system problem rather than a one-time task. So existing solutions have three forms. Mathematical synthesis can find strong schedules, but combinatorial search may take minutes to hours as cluster grows. Analytic heuristics are fast, but they rely on the symmetric and simplified hardware models. And production deployments therefore still depend heavily on experts who design patterns and tune them through trial and error. Automated methods mainly fall into mathematical optimization and analytical heuristics. The former faces NP-hard formulations and often needs human-provided communication sketches to limit the search space, and the later is efficient under regular topologies, but suffers from rigid assumptions and a model-to-hardware gap where contention, interference, or topology changes. So the existing model is struggling in production because of the dynamic settings, the large search space, and the reality gap. So we summarize three limitations. First is the computational inefficiency as the scheduling space grows. The second is the dependence on human guidance, which limits the solution diversity. And the third is the absence of real hardware feedback, so model prediction errors cannot be corrected. So this motivates our question: can we combine efficient exploration with hardware faithful validation? So here, LLMs are promising because they can generate the answer rapidly and propose diverse structures using raw knowledge of communication patterns, parallel programming, and system code without human guidance. Their multi-turn interface also make it natural to incorporate execution result and refine later proposals, enabling feedback mechanism. But directly generate MNCCL XML is unreliable. The schedules can contain thousands of lines, highly cross-referenced fields, strict dependency ordering, and detailed hardware resource assignments. One small syntax or semantic error can invalidate the whole program. So we need the LLM's exploration ability without asking it to solve every correctness critical detail. So here our key insight is to separate the intent from execution. The LLM generates only data movement logic, which chunks move, which GPU send and receives. Deterministic algorithm then assign channels, thread blocks, and instances. This greatly reduced the LLM output space and combine creative high-level exploration with reliable low-level realization. So based on these concepts, we propose OptiFlow to optimize the collective communication algorithms iteratively. OptiFlow is composed of four components: a prompt organizer, an LLM plan generator, a deterministic plan translator, and a instruction executor. No model training or gradient updates is required. So let me briefly walk through these components. First is the prompt organizer. So the prompt contains three kinds of information. The initialization defines the operator, the message size, topology, hardware, and a simple ring plan as a starting point. Only historically improved solutions are permanently retained, keeping context short and useful. Finally, the feedback of last turn encouraged broader exploration instead of repeatedly sampling the same design. Second, the plan generator uses this prompt to produce DSL instructions rather than the final low-level schedule. So the DSL describes the chunk-level data movement. The example DSL instruction means transferring chunk J of node I from GPU K to GPU L, which intentionally omits the timing channels and thread blocks. A short Python program expands the patterns and reducing the syntax error and the token cost, while preserving high-level reasoning about rings, gateways, and hierarchical exchange. And third, the plan translator receives these DSL instructions and generates executable MSCCL XML schedules. This is where high-level LLM output becomes a grounded system implementation. So the plan translator employs a series of deterministic algorithms, including a linear mapping ones and a greedy chain decomposition heuristic algorithm, which constructs directly transmission trees and decomposes them into disjoint chains for each data chunk. Thus, different chains use separated resources, preserving valid dependency ordering. This guarantees executable schedules while allowing the LLMs to focus only on the communication structure that benefits from the creative exploration. And finally, candidates schedules run on a physical GPU cluster. The executor measures actual communication latency and captures the runtime error. These ground truth results are returned to the prompt organizer, closing loop and correcting mismatches that an abstract performance model would miss. So validation produces three outcomes. Better valid plans enter the selected history and update the current best. The invalid plans return errors traces for the next turn repair. Duplicated plans trigger stronger exploration and higher sampling temperature. Together, these mechanisms support performance improvement, automatic correction, and search diversity. So we evaluate the OptiFlow altogether on 8, 16, and 32 A100 NVIDIA GPUs with messages from 1 kilobytes to 1 gigabytes. Baselines are production NICO and two synthesis systems, TACCL and TECCL. All synthesized schedules use the same MSCCL version. So OptiFlow consistently outperforms the baselines across the evaluated configurations. It achieves up to 3.75 times up to speed up over NICO and 5.12 times over Tahoe and 3.28 over TECCL. For LM relevant sizes from 1 megabytes to 1 gigabytes, OptiFlow gains 1.55 times on one node and 2.19 times across nodes. OptiFlow also scales better in optimization time. Across 8 to 32 GPUs, its runtime grows moderately because LM inference and deterministic translation remain nearly constant. The mainly time cost, real hardware evaluation, scales with the cluster size. And in contrast, the mathematical formulations frequently exceed the 4-hour limit on larger asymmetric multi-node cases because their search space grows rapidly. And I will briefly illustrate one discovered 16 GPU algorithm. In phase 1, the GPU first exploits fast NVLink to synchronize data locally. And in phase 2, selected GPUs act as gateways and exchange data across the IP switch. This concentrates cross-node traffic while remaining parallelism. And in phase 3, gateways broadcast the remote chunks within each node. The OptiFlow discovers a topology-aware global local decomposition, achieving about 3 times faster than NICO. So to conclude, the collective algorithm optimization is increasingly dynamic and expensive. OptiFlow separates LLM generation data movement intent from the deterministic scheduling logic, and the real hardware feedback closes the iteration optimization loop. It defines better algorithms and scales better than the optimization-based baselines. And the future works include larger asymmetric clusters, simulator-assisted validation, and more collective optimized operations. So thank you very much for your attention, and I welcome your questions and comments.
Thank you, Peng, for the wonderful talk. Any questions? The audience?
Very nice talk. I was curious about the validation.
Yes.
The hardware validation. Some of it is done on a test bed today, right? And you said about using simulators in the future. So how closely does the simulation or emulation environment have to track real production environments to be able to get really good speed ups?
Maybe we can use some flow level simulators. It can replace the real hardware deployment. This is especially important because when we scale up to like thousands of GPUs, because very often we don't have these hardware resources, so we have to use the simulators to replace to get the output from the for the productive environment. So currently for the 1,000 GPUs level, the packet level simulators may be very slow. Like for one single experiment, we have to spend hours of times to wait for the result. And for the flow level simulator, maybe we have to more faster, like seconds or even less than 1 second to get the result, and enable us to make a very fast loop to optimize the algorithm.
Thank you.
Any other questions? Let me ask, you mentioned as the future more evaluating some topologies. Any comment on what topologies you want to consider this evaluation?
Actually, for now, well, we can only access the topology of 32 GPUs. That is, we can say that is a rather simple topology. For larger data center networks, we can do more experiments, especially in the simulators for other new productive topologies like factory or real optimized factory or other things.
Thank you. So let's thank the speaker again, and we will move on for the third talk. And this is about the balancing in RDMA. The speaker is Wang. Is he here? Thank you. So Wang is first year PhD student in computer science at Memorial University of Newfoundland in Canada. The research focus is on data center networks.